So we're going to look at Unit 7, Lesson 1. And I want to exhibit this problem for you, 7 to the 4th power. What is this notation and what does it mean? So 7 to the 4th power is just a way to write 7 times 7 times 7 times 7. So it's a way to write multiplication in another way. So we've got our warm-up question here. Which one does not belong? So if we evaluate 2 to the 3rd, that would be 2 times 2 times 2. And if we multiplied that, that would be 8. 8 is 8. If we evaluate 3 to the 2nd power, that would be 3 times 3, which is 9. And then we've got this one, that if we evaluate 2 times 2, that would be 4. And 2 to the 1st is times another 2, which would be that 4 times 2 is 8. So we've got 3 of these, this one, and this one, that have, if we evaluate them, they would have a value of 8. So for that reason, we could say 3 to the 2nd doesn't belong because it's the only one that doesn't have a value of 8. We could also look at some other ones of these. You know how much I love these, which one doesn't belong, because we could choose most of these if we have good reasoning. So we've said this one could be different because it has a value of 9. This one, what's different about that one? The 8 is different because it's the only one that doesn't have an exponent. So we could say that one doesn't belong because it's the only one without an exponent. We could say that this one is the one that doesn't belong because of the multiplication symbol that it uses right there. It's the only one that has an expression with a multiplication symbol there. The rest of them are just using exponents or plain old numbers. So depending on your reasoning, you could pick any of those. We've got an example here of, in the lesson, reviewing exponents is the point of this lesson. May and Andre found an old brass bottle that contained a magical genie. They freed the genie and it offered them each a magical dollar coin as a thanks. The magic coin turned into 2 coins on the first day. The 2 coins turned into 4 coins on the second day. On the 3rd day, the 4 coins turned into, magically, 8 coins. And this pattern continued for 28 days. May was trying to calculate how many coins she would have. And remember that instead of writing 1 times 2 times 2 times 2 times 2 times 2 times 2, for the number of coins on the 6th day, she could write 2 to the 6th. The number of coins May had on the 28th day is very, very large. Write an expression to represent this number without computing its value. And if you are thinking that would be 2 to the 28th power, you would be correct. Andre's coins lost their magic on the 25th day. So Andre only doubled his coins for 25 days. So May has a lot more coins than he does. How many times more coins does May have than Andre? So if May has, and that's really hard to read there, what I wrote for number 1, but it says 2 to the 28th. If May has 2 to the 28th coins, but Andre has 2 to the 25th, May has 2 to the third, and we evaluated that in our warm-up as 2 times 2 times 2, which is 8. We could also use exponents with fractions. So after a while, Jada picks up a coin that seems different than the others. She notices that the next day only half of the coin is left. On the second day, only 1/4 of the coin is left. On the third day, 1/8 of the coin is left. Remains. What fraction remains after 6 days? So if you're thinking, you could write it like this. 1/2 in parentheses to the 6th power, you'd be correct. What fraction of the coin remains after 28 days? If you're thinking, you would write that as 1/2 to the 28th power, you'd be good. You'd be correct. Does the coin disappear completely? If so, after how many days? So I'm going to let you guys think about that one and answer that one on your own. And here's the little applet that goes with that. I'll let you guys watch this coin as it disappears. There we go. So you'll see at the 10th day, there's still a little sliver left. It doesn't disappear completely. Tyler has 2 parents. Each of his parents also has 2 parents. Draw a family tree. We're talking about a traditional family tree here, showing Tyler, his parents, his grandparents, and his great-grandparents. So if we've got Tyler at the bottom, Tyler has a mom and a dad, and each of those parents had a mom and a dad and a mom. Dad had a mom and a dad. So right here, this is in the blue, the light blue is Tyler's parents, and the green is Tyler's grandparents. So if we go back one more generation, each of these had a mom and a dad. Mom, dad, mom, dad, mom, dad. So this is Tyler. Then we've got his parents. Then we've got his grandparents in green. And then in purple, we've got his great-grandparents. So that's just a real-life example of exponents there. All right, I'm going to give you guys a copy of this on paper. And you're going to write these expressions using exponents for problem 1. And then number 2, problem 2, you can type those into your calculator and evaluate those expressions. There's problem 3. We've got some review questions here. So hopefully that'll keep some things fresh in your brain. And that is all we have for today. Thanks for